Patrick, you are the boss. You are telling me.
Okay, so welcome to this session. We have two papers. The first one is going to be presented by Bruno. And I don't know about the second one. Is it Jorn who presents? Well, we'll start with Bruno for this full paper.
Okay, thanks, Patrick. Thanks to all for attending. So I'm going to present a joint work with our beloved station chair and a former PhD student, Ximun Castoreo. So it is in line with our general work on network neutrality. But here, what we want to emphasize is that if rules are passed about neutrality, then we really need monitoring tools. But on the other hand, those tools' accuracy, it also needs to be investigated because service provider can play with the tools to apply service differentiation at some extent and still evade detection. So very briefly, it's a slide that I often present, so some historical reminders about neutrality. So network neutrality debate, for those who don't know it, it started in 2005, approximately when the CEO of AT&T raised the issue that distant providers, they use AT&T network without paying anything for it. And in order to keep some revenue, so they complained that that those distant providers should pay for it at the risk of being differentiated, if not paying. So this raised a lot of protests worldwide from user association, content providers, and so on. So that's the main reason of the network neutrality debate. So there are many other complaints about that. So I just list here two of them, but there are many, and actually this doesn't stop. So there are rules that are passed worldwide. So I here just present one of the rules coming from Europe, actually from the European Parliament in 2014. So the definition of network neutrality, according to the European Parliament, is the principle which means that traffic should be treated equally without discrimination, restriction, or interference, independent of the sender, the receiver, the type, content, device, service, or application. So with some exceptional case where service differentiation could be applied. So just in case of temporary congestion, in terms of security attack or legal action and so on. So it's something that is existing in many different countries. But still, the debate is not closed because, as here I list that there are many new public consultation even after rules are passed, because there are many gray zones that have to be tackled. So many new issues that are raised related to network neutrality. So I list here four of them. The first one is a well-known zero rating or sponsored data issue in mobile communications, where content providers can pay for some content providers can pay for the traffic that is going through your mobile, such that it doesn't enter your data plan. Other issues are related to vertical integration, about the different ways to bypass the packet-based neutrality and still apply differentiation, such as when you use content delivery networks, and so on. And the debate is still very active since Donald Trump administration voted to repeal network neutrality in the US, which creates some differences worldwide that we also studied in previous papers, and particularly one that we probably presented in GECON during the past years. Okay, So this is the general idea about network neutrality, but the purpose of this talk is actually to look at the different tools, and particularly one tool about this neutrality compliance. So in order to be sure that neutrality is respected by internet service providers, so we need monitoring tools. Actually, there is a very limited list of tools for that, and most of them are academic tools, and they study a very limited amount of neutrality infringement, and they are really barely maintained. Some of them are not maintained anymore; they are not even reachable anymore, and even theoretically, they are based on statistical tests that don't have any theoretical ground. So it's if you want to complain about an ISP not respecting neutrality, you cannot do it in court because so mathematically the tools are not very good. So among those tools, actually there is one on which we are going to look more closely at. It's Wehe, that is co-designed by ARCEP, the French regulator, and Northeastern University. So that's one of the single tools that have been co-developed by a regulator, and we really believe that that's a really good way to proceed, to have such a monitoring tool such that it can be maintained during a long period of time. And I just want to mention that recently BEREC, the Association of European Regulators, is also defining a tool that you can find on this GitHub link. So you will be able to click when I will distribute when the slide will be available. So our goal, particularly in this talk, is to design a test bed to evaluate this Wehe tool and its detection capacities, and then to investigate if there is room for differentiation for an ISP when this tool is applied. Is it possible for an ISP to maximize differentiation to have an impact while still avoiding Wehe detection? So that's something that we want to investigate. So a brief description of Wehe. So as I said, this is a tool that was developed by ARCEP, the French regulator, and Northeastern University in the US. So you can find it on the Play Store, App Store. And it can be directly applied to test the main applications, Netflix, Spotify, Amazon, and YouTube, and so on. And what it does, it tests the throughput of the different applications and check if it is differentiated. So the code is available on the web, and if you want to test other traffic, and that will be what we did. So the basic principle. So I here describe two screenshots of the application. Wehe application is if you download it from on your smartphone. So the basic idea is to replay a pre-recorded traffic between a client and a Wehe server. Okay, so that's why you have pre-recorded traffic of those type, but not only. So the first replay is identical to the original traffic, and the second replay is the same type of traffic but encrypted, so that it cannot identified, and an ISP could not differentiate from it. And it compares the two received files to test if they are treated differently. So as I said, the mathematical test is not that good mathematically, but one of the good points is that it's probably very conservative, so that you are probably limiting the case of false positive. So here an example of what it gives when you have a differentiation that is detected here for YouTube. So what's the test bed that we have built? So we have designed a test bed based on a simple topology where we have 3 different components. First, the client side, the server side, and the core network side. So, and the core network is emulated by a single device, a middle box that is running a Linux traffic control utility with a NetM queuing discipline. So this middle box is somewhat mimicking the network bottleneck, if any. So this is a simple topology that is helpful to capture the main differentiation features. So with on our middle box, so we are able, if we wish, to apply some service differentiation where we can control which service differentiation, which can be based on throughput limitation, on packet loss rate, or on delay. So we are trying the 3 types of differentiation, and we are going to compare them. And the experiments that we are going to make in an extensive way is in the case of a transfer of a 1 GB file, and also video streaming, but in a more limited situation. So that's something that we are going to pursue as the next work. And we are multiplying the test to get some statistics about the probability of detection. So here is a snapshot of what we can, how it proceeds. So first, for our 1 GB file transfer, what are the possible range of differentiation for the 3 different policies in terms of differentiation that I described: throughput limitation, packet loss, and delay. So here I describe the interval over which detection is larger than 0 and smaller than 1. Otherwise, it would be complete detection or complete non-detection. So you can see that for the 1 GB file transfer, you have a detection with a non-negative and not 1 probability if you limit the throughput around 90%. You have a detection that is becoming present if you induce a packet loss of between 0.2 and 0.5%, and if delay is if your packet transfer are delayed by around let's say 20 milliseconds. And for video streaming, we are able also to obtain some similar curves, but with interestingly a bit different values, especially in terms of packet loss. So how do we use that to see if there is a good economic strategy for an ISP which is being monitored by Wehe? So the question is, given the detection threshold that we have just described, is it still valuable to differentiate? And what is the best differentiation strategy for an ISP? So we have designed a mathematical model for that. And so we describe the utility of the ISP by this quasi-linear expression, where the utility is the gain that you have from detection, where D is the quality degradation due to differentiation, and G is a marginal gain that is expressing what you are earning from a degradation for this application. And you have this gain minus the cost, and the cost is a cost of detection multiplied by a function of the probability detection. So we decided, we chose x divided by 1 minus x. So that is an increasing function with cost 0 if there is a 0 probability of detection, and infinity if you have a detection of probability 1. And we also define U tilde as the normalized utility, where you just divide by G, so that you have just, instead of having two parameters G and S, you have just one parameter S divided by G. And we are going to study what's going to happen for our 1 GB file transfer. So the metrics that we are using for the quality degradation is the relative transfer time increase, which is the difference between the time of the transfer time when differentiated minus when it's neutral, when there's no differentiation, divided by the transfer time when it's neutral. So if we first look at the impact of the 3 differentiations on the degradation level D, so you can see this those value curves that that are obtained from simulation, and for the different ranges of differentiation where detection was starting. And now, if we combine those curves with the previous one, we can obtain some interesting expressions. So here we draw the probability of detection in terms of the relative transfer time extension, D. And you can see here that degrading throughput allows to extend transfer time by nearly 10% without being detected by Wehe, while it comes much earlier for delay and packet loss. So it's about 2% delay-based degradation before being detected, and 2% loss based degradation probability here in this case. Okay, so throughput degradation is actually a better strategy for ISPs. So now, if I look at the optimization of the normalized utility function, so I draw the utility in terms of the differentiation thresholds, and I try to optimize the different values. So just trying to optimize my utility function in terms of the parameter of differentiation. So I can see for different values of S over G, so it's the relative gain with respect to the cost. And for example, for S divided by G equal to 0.01. So you can see that at the optimal differentiation level, the throughput is just obtained as about 90%, and the utility is larger than 0.1. At the optimal loss rate degradation, it's obtained as 0.4%, but then the utility is lower than it's about half of the utility when I degrade optimally the throughput, and it's even worse when I degrade delay. So for the specific case of file transfers, so affecting the throughput is actually the most effective thing. So as conclusions, so what we have done is we have designed a test bed to analyze network neutrality monitoring tools detection, so something that we would like to extend. And we are able to understand among 3 differentiation strategies which one is the most efficient for an ISP, trying to still differentiate service while avoiding and evading detection. So what are the next things that we would like to study? So first, we would like to, what we have done so far is deeply is the case of the analysis of file transfer. So we would like to carry out the same type of analysis for other types of traffic. So we have started to do it for video streaming, but then we need to define a utility function that corresponds to video streaming, and that's something that we are thinking of, trying to look at the notion of quality of experience. So that's something that we would like to do right now. And we would like to extend also the testbed to some kind of more complex topologies and a single middle box to represent the network. So that's it for me. Thanks for your attention, and I'm going to end the recording, I guess.